All right. So we are going to study a new conceptual random variable, and this is just going to be the most important continuous random variable that you are going to learn. So the name of the random variable here is the normal random variable, and it has a great essence in further statistical studies. Therefore, we are going to spare a little more time on this. So we are going to explain the normal random variable in many detail. The normal random variable is also called a Gaussian random variable, and it is named after the famous mathematician Carl Friedrich Gauss. So actually, there are resources which are telling us that the normal random variable is not actually invented by Carl Friedrich Gauss, but some other scientists. But still, Carl Friedrich Gauss contributed so much on the theory of the normal random variable. Therefore, the name of this random variable is given after his name. But usually in literature, everybody calls this random variable the normal random variable. So just like the other continuous random variables that we have studied, continuous uniform random variable and the exponential random variable, we will start by introducing the probability density function of this random variable. And unfortunately, this function is a little complicated. So the probability density function of the normal random variable is 1 over sigma times square root of 2 pi times e to the power of minus, in the numerator we have x minus mu square, and in the denominator we have 2 sigma square. Okay, so if a continuous random variable has a probability density function in this form, then we call this random variable the normal random variable. Now, one thing that you need to notice at this point, this probability density function is defined for all real values. Now, you see, a continuous uniform random variable can only take real values between the boundaries. We determine the lower bound and the upper bound parameter for the continuous uniform random variable, and the random variable can only take values between these two values. Or an exponential random variable can only take non-negative values, if you remember. But a normal random variable theoretically can take any real value from minus infinity to plus infinity. Therefore, it has no boundaries. However, it has parameters. So we have two unknown values here in this function, which are mu and sigma. So we have mu in the numerator of the power of the exponential function, and we have sigma in both parts, in the denominator of the multiplier term and also in the denominator of the power of the exponential function. So mu can take any real value, and sigma can only take positive values. Remember, a probability density function can only be a non-negative function, and if sigma here is negative, then this function would also be a negative function. Therefore, it is forbidden for sigma to take any negative value. It cannot be zero either. However, mu can take any value. So it has two parameters. This normal random variable has two parameters. Mu is called the location parameter and sigma is called the scale parameter. We are going to explain why they are named like this, why we are using the wording location and scale. Now, at this point, you need to know that these parameters can take arbitrarily any value as long as sigma is positive. And depending on your choice of mu and sigma, you would get a different normal random variable. Another important point you need to realize about the probability density function of the normal random variable is that the power of the exponential term here is a quadratic function. So it is a second order function of variable x here. Remember, in the exponential random variable, the power of the exponential term was a linear function because the function was, let me show that function to you, lambda times e to the power minus lambda x. So the power of the exponential term was a linear function of x. However, in the normal distribution, in the PDF, the power of the exponential term is a quadratic function or a second order polynomial of x. So this actually distinguishes a normal random variable from an exponential random variable. So we have such a weird function actually, and of course you do not need to memorize such a function, but we need to draw this function and understand its shape. But before that, let me repeat again, these mu and sigma values in the probability density function are called the parameters of this normal random variable. Mu can take any real value. You can determine the mu value as you like. However, the sigma value, the scale parameter, can only take positive values. Otherwise, the probability density function would be negative. And therefore, if we want to define a normal random variable, we need to define its parameters first, the location and the scale parameter, or mu and sigma values. And we represent this realization, this definition of this normal random variable in the mathematical terms. X is normally distributed with location parameter mu and scale parameter sigma. So it has two parameters. This is the mathematical expression of the definition. Now, which mu value you choose, which real value for mu or which positive real value for sigma you choose, it does not matter. The total area under this probability density function will always be equal to 1. So if you integrate the PDF of a normal random variable, independent of your choice on the location parameter and the scale parameter, the total area under this PDF will always be equal to 1. Now, at this point, we are ready to draw the probability density function of a normal random variable. So this complicated function with mu values in it and sigma values in it, and also the famous pi value, and also there is the Euler number, the exponential number. So we have this weird function, and if you want to draw this weird function, you are just going to get a shape like this, which looks like a bell. So therefore, the normal distribution's probability density function is also called the bell-shaped curve. Now, most of the students always ask this question, are you going to apply the bell curve when you are grading the students? Now, you see, bell curve grading is very related to the normal random variable. So if you want to understand the bell curve grading, you need to understand the normal distribution and the normal random variable first. Now, if you draw the normal random variable, it is going to have a bell shape like this. From minus infinity to plus infinity, the function will be defined like this, and the maximum point will be attained at mu. Because as you can see, in the probability density function, exponential function of a negative value will always be less than 1, right? Because of minus sign in front of the power will make this exponential value always less than 1, except when x is exactly equal to mu. In that case, e to the power 0 will simply equal to 1. Therefore, when the variable x here takes the value of mu, then this function will be maximized. It is therefore the maximum is attained at the location parameter. So the probability density function of the normal random variable is maximized at the location parameter, and because we have x minus mu square here, depending on the distance of x to the location parameter, the function is just going to decrease, and whether x is greater than mu or less than mu, if the distance is the same because of the square term here, the function will yield the same value. Therefore, this function is also symmetric around the location parameter. So this probability density function of the normal random variable is symmetric around the location parameter, and it is also maximized at the location parameter. Now, if the x value moves far from the location parameter, the function will be decreasing, and because of the exponential term, it is just going to decrease so fast. In fact, it is just going to converge to 0 after you move 3 or 4 scale parameters away from the location parameter. As you can see, if you move 1 scale parameter from the location parameter, either on the right-hand side or the left-hand side, the function will decrease. If you move 2 scale parameters away from the location parameter, the function will decrease as well. But if you move 3 scale parameters away, in that case, the function will become too close to 0. But the actual convergence will occur in the infinity. Because of the exponential term in that function, the convergence is going to be very fast, but it is just going to converge to 0 at infinity. So at both extremes, at positive infinity or negative infinity, the function will be 0. And of course, there will be an area under this function that is accumulated from minus infinity to plus infinity, and that area is just equal to 1. So the total area under this bell-shaped curve is equal to 1. Now, there is a special situation of the normal random variable. If you choose the location parameter mu as 0, and the scale parameter sigma as 1, then the resulting normal random variable will be called a standard normal random variable. Now, we are always using capital letters to denote the random variables, and so far we have used X, W, T, Y, many capital letters to denote the random variables, but in order to denote a standard normal random variable with location parameter 0 and scale parameter equal to 1, the literature, the textbooks will always use this letter Z. So a capital Z will always represent a standard normal random variable with location parameter 0 and scale parameter 1. So if you write Z is normally distributed with 0, 1 parameter setting, this means the location parameter is 0, mu is 0, and sigma is 1. Now, if we just go back to the probability density function of a normal random variable, if we plug in mu value as 0 and sigma value as 1, then this probability density function will be simplified to this form. So it will just become 1 over square root of 2 pi e to the power minus x squared over 2. Again, this function will be defined for all real numbers, and it is just going to be a probability density function, but of standard normal random variable. And there is a special letter that we use to represent the probability density function of a standard normal random variable, which is the lowercase phi letter from the Greek alphabet. And phi of x is equal to 1 over square root of 2 pi e to the power minus x squared over 2. This is the spatial probability density function for the standard normal random variable when the location parameter and the scale parameter are set as 0 and 1 respectively. So why have we implied the standard normal random variable? Because it is very important for studying the normal random variable. Standard normal random variables are the simplest form of a normal random variable, and if we can understand and calculate the related probabilities on this standard normal random variable, then we will be able to calculate any probability question related to other normal random variables. So standard normal random variable will be the first thing that we are going to learn. Now, if we want to draw the probability density function of the standard normal random variable, the shape is just going to be the same as the shape of any normal random variable. Again, you will see a bell-shaped curve. However, because the location parameter is defined as 0, the probability density function will be maximized at 0 and will also be symmetric around 0. And because the scale parameter is equal to 1, the convergence of the tails of this bell shape, we call these parts of the function tails or the extremes. So the tails of this function converge to 0 approximately when you pass minus 3 and plus 3. So the most of the area under the function will be between minus 3 and plus 3 here. Okay, the rest is very small. So this means what? Remember, a probability density function shows the relative realization likeliness of that random variable, right? If the probability density function is greater at any point, then the random variable is going to take a value around that point more likely, but if the probability density function is less, so it is less likely to realize that random variable with a value from that point. Now, according to this picture, even though theoretically standard normal random variable can take any value from minus infinity to plus infinity because of the small probability density values in the tail parts, practically it is very, very less likely for a standard normal random variable to take any value above 3 or less than minus 3. I'm not saying it is impossible, it is possible, but I mean, you can only see that with a very, very small probability. So even though theoretically a normal random variable can take any real value, practically it has a very small probability to take any value which is far from 3 scale parameters away from the parameter. All right, now we can talk about the cumulative distribution function. So because if you are going to solve any probability question related to a continuous random variable, you definitely need to know its cumulative distribution function. Remember, for continuous random variables, in order to calculate interval probabilities, we were integrating the probability density function. So the first thing that we need to do is to determine the cumulative distribution function, or CDF, of the normal random variable, which is again denoted as capital F of X, and it is representing the probability of that random variable to be less than or equal to X. Actually, this means the cumulative probability up to X. So what is the probability of our random variable to take any value from minus infinity to lowercase x? Now, in order to calculate this probability, you need to calculate the integral of the probability density function of the normal random variable from minus infinity to x, of course, by changing the variable and the integral operator to t. Now, the unfortunate situation about this integral is that it is not solvable. Now, there is not a closed form solution for this integral, okay? If you can find one, then you will win the Nobel Prize. It is very important, but it is impossible. So there is not a theoretical solution for this integral. So what are we going to do about this? Because if we cannot solve this integral, we cannot calculate this probability. And if we cannot calculate this probability, how come we can use the normal random variable to model the real life variables? So what are we going to do about this? Even though there is not a theoretical solution for this integral, we can use numerical methods such as Simpson's integral rule. There are many numerical methods which can calculate unsolvable integrals. We can use these numerical methods to approximately calculate the CDF. Not the exact solution, but a very, very close solution to that. The error that we are going to make from there is just going to be very insignificant. Therefore, we can use that numerical methods to calculate the approximate probability for this, or we can calculate approximately this integral with a numerical approach. Okay. Now, so at this point, we should say that theoretically there is not a solution for this integral, but numerically, practically, we can find an approximate solution for this integral by using a numerical method. Now, remember, we have used the lowercase Greek phi letter to represent the probability density function of the standard normal random variable. And again, for the standard normal random variable, we are going to use the capital phi letter from the Greek alphabet, which is representing the probability of the standard normal random variable z to be less than or equal to x, and which is calculated by integrating the standard normal probability density function from minus infinity to x. And that is just going to be represented by the capital phi of x. Again, this integral is not solvable either. However, we are representing this integral with capital phi of x. Now, we are going to learn how we can compute such cumulative probabilities in the future videos. So at this point, let's draw the cumulative distribution functions. Now, if we just go back the first PDF that we have drawn for the normal random variable. Now, as you move from left to right, please just focus on the accumulated area under the function on the left-hand side. So at minus infinity, there is not an area that is accumulated. So as you move, the area will accumulate, but so slowly. But when you arrive to -3 scale parameters away from the location parameter, the area on the left-hand side will start to accumulate significantly. Again, at first slow, but then it is just going to be very fast to accumulate. And when you just reach to the location parameter, half of the area under the curve will be accumulated on the left-hand side of the location parameter. So which is exactly 0.5, because the total area under the function is 1. And as you move in the direction of plus infinity, the accumulation will continue. The total area will be even more than 0.5. Then as you move a little further, 3 sigmas away, 3 locale parameters away from the location parameter, the accumulation will be reaching to 1. And even if you move from here, the accumulation will almost converge to 1. And when you reach to infinity, the total area will be accumulated, and the total area is simply 1. So because the cumulative distribution function is the representation of this accumulated area, the cumulative probabilities, its shape is just going to be looking like this S shape. So this S-shaped curve is the behavior of the CDF of a normal random variable. So on the left-hand side, you see the cumulative distribution function of any normal random variable. As you see, the probability that a normal random variable to take a value that is less than its location parameter is 0.5. And it starts to significantly increase when it comes very close to -3 scale parameters, sigmas, and it will just converge to 1, almost converge to 1, when you get +3 scale parameters away from the location parameter. For the standard normal distribution, the cumulative distribution function will exactly look like the CDF of any normal random variable. However, this time the probability accumulated in this function will be equal to 0.5 at the location parameter 0. So in the standard normal PDF, as you can see, the probability of or random variable to take any value that is less than 0 will be basically the area under the function on the left-hand side of 0, which is half of the area, and therefore it is 0.5. And one more thing, again, even though practically this function is very close to 0 at -3 sigmas away from the location parameter, practically the convergence to 0 of the CDF occurs at -infinity. And again, theoretically, the convergence to 1 will occur at +infinity. So this function will never touch to the horizontal line of 1 or horizontal line of 0. It is going to converge to these points at infinity. So theoretically, the normal random variable can take any real value, but practically, because of the exponential function in the probability density function, it is very, very, very less likely to get two extreme values.